Today we're from Group 2, Calculus 1C class of Mosh, going to present Chapter 13 of Sequence and Series. Our member is Kentaro Tanaka, Nadia Audrey Salim, Keith Tran, Robin Chang, George Dianda, and Beverly Leslie Tanada.
In Chapter 13 of Sequences and Series, we will learn about the following: sequences and series, the test performed, the radius of convergence, the Taylor series expansion, decomposition, substitution, integration, differentiation, combination, as well as application.
First of all, we're going to talk about sequences and a series explanation. Sequence again are a function that has natural numbers as its independent variable, and each value of sequence is an element of complex numbers. That basically a list of numbers like 1, 2, 3, 4, 5, stuff like that. Sequences similar to functions that approaches a number are called converging series. So when limit an as n goes to infinity is equal to a number which is converging series, and a converging sequence. Sequence that doesn't approach a number or approaches infinity is called diverging sequence. Series explanation. Series sigma an is basically a sum of sequence, and it is analogous to evaluating an integral. A series similar to evaluation of an integral that approaches a number is called converging series. A series that doesn't approach a number is called diverging series. Squeeze theorem. There are three functions, g of x, h of x, and f of x. If the sequence g of x is less than h of x, and h of x is less than f of x, all number n is bigger than n, and limit g of x as n goes to infinity is equal to limit f of x n goes to infinity is equal to L, then by squared theorem we can get limit h of x as n goes to infinity is equal to same as L. So there is an example. We have limit arctangent of n as n goes to infinity, then is equal to arctangent of infinity, which is pi over 2. So if we think about the graph, the arctangent is pretty close to pi over 2. So in this another example, we have limit -1 to the n squared minus 1 over n squared as n goes to infinity. So we basically get this limit is equal to 1, but -1 to the n does not let the sequence approach a single number, hence the sequence diverges.
Theorem to also keep in mind is that if the limit as n approaches infinity of the absolute value of an equals to 0, then the limit as n approaches infinity of an also equals to 0, hence shown by the graph.
Next, we will talk about tests performed to see if a series converges or diverges. The first test we perform is a zero test. If a series does not approach zero, then it is considered diverging. So limit as n approaches infinity of an does not equal to zero, then the power series an diverges. This is because if a function approaches a limit that is not zero, then the area under the curve increases larger and larger as x approaches infinity. In this example, we take the power series from 1 to infinity of e to the power of n over 2 to the power of n, and to find out if this series diverges or converges, we apply the zero test. So limit as n approaches infinity of e over 2 to the power of n approaches infinity. Since the limit does not approach zero, the series diverges. Test number 2 is the geometric series test. From pre-cal, we know that this is the form of a geometric series. If we take this and split it up into this equation, and if absolute value of r is greater than 0 but less than 1, then the sum will be a finite number. Hence, the absolute value of r is greater than 0 or less than 1, it converges. And if the absolute value of r is greater than or equal to 1, it diverges. In the example of power series 1 to infinity of 2 times 1/3 to the power of 2n, we could change the equation to a geometric series form. So power series 1 to infinity of 2/9 times 1/9 to the power of n minus 1. Since r equals 1/9 and the absolute value of r is greater than 0 but less than 1, the series converges. Test number 3 is a hyperharmonic series test. This comes in the form of power series 1 divided by n to the p, where n starts from 1. If p is greater than 1, then the series converges. And if p is less than or equal to 1, it diverges. If p equals 1, it is considered a harmonic series. In the example of power series 1 to infinity, we have 1 over n to the power of 3/2. Since p is equal to 3/2, p is greater than 1, so the series converges. Test number 4, the telescopic test. Telescopic method is a series whose partial sums eventually only have a fixed number of terms after cancellation. We use partial fractions to expand the series. We use the table on the right to know if the summation of the series or subtraction of the series converges or diverges. In this example, p series of 2 to infinity of 1 over n squared minus 1, we use partial fraction decomposition and we end up with this equation. We then use this to expand it and end up with like terms which we can cross out and end up with the answer of 3/4. Test number 5, the ratio test. We let the power series of an be a positive term series, then we can apply the ratio test. So we take the limit as n approaches infinity of an plus 1 divided by an equal to r, and if r is greater than 1, series diverges. If r is equal to 1, we have no conclusion and must apply a different test. If r is less than 1, then the series converges. In this example, we have the power series of 2 to infinity of n plus 2 factorial divided by n minus 1 factorial times 2 to the power of n. We use the ratio test and find that the limit as n approaches infinity of an plus 1 divided by n, we get like terms which we can cross out and end up with the limit as n approaches infinity of n plus 3 divided by 2n, which is equal to 1/2. Since r is equal to 1/2 and r is less than 1, the series converges.
For test number 6, we use a root test. We're gonna take the n root of the power series. If the limit of that go from n to infinity, end up with the number, and that number, if that number will larger than 1, the power series will go to diverges. If equal 1, we have no conclusion for that. If it like less than 1, the power series will converges. Example, the power series go from 1 to infinity of n minus 1 over n squared to the n, and we take the n root of that, and we will end up with the limit of n minus 1 over n squared. This limit go from n to infinity equal 0, and 0 less than 1, so the series converges. Test number 7, we use the integral to test on the power series. Let the power series an be changed to the integral function of fs ds. If the integral equal to the infinite number, the power series diverges. If the integral equal to infinite, the power series will converge. For example, the power series go from n to infinity of n over n squared minus 1. We take the integral of that and use the substitution u equal x squared minus 1, and then we get 1 over 2 limit of natural log u, and that limit will go to infinity. Therefore, the series diverges. Test number 8, comparison test. Let the power series of an and bn be a positive term series with the bn that we can choose. If an less than or equal bn, with an diverges, we get bn diverges. If bn converges, we get an converges. Okay. For example, the power series of 1 over n times n plus 2. We know that 1 over n squared plus 2n are less than 1 over n squared. And since 1 over n squared converges, we get this power series converges. Limit comparison test. If the limit n go to infinity of an over bn, with bn is we can choose equal to a non-zero number, and bn converges, an will converges. If bn diverges, an diverges. Test on the power series of 1 over n times n plus 2. I will choose 1 over n squared is my choice, and it will end up with the limit of n squared over n squared plus 2n equal to 1. And we know that 1 over n squared converges, so the series converges.
We will learn about alternating series. An alternating series is a series which terms alternate. It will be in the form of power of series minus 1 to the power of n times an. We also have two conditions to conclude if a series is converging or not. The first one is an plus 1 is less than or equal to an. The second condition is limit of n to infinity of an is equal to 0. If the series is converging, then we have to check two conditions. If power of series of absolute an converges, then series absolutely converges. If power of series of absolute an diverges, then the series conditionally converges. From a given sample problem below, we need to check if the two conditions are fulfilled. Since it is fulfilled, we then need to apply a test. Here we use the comparison test. Since 1 over n to the power of 3 over 2 converges, the series absolutely converges.
Of convergence. First of all, we need to define the definition of radius convergence. In general, there is always an interval go from negative R to the positive R in which the power series converges, and the number is called the radius of convergence, while the interval itself is called the interval of convergence. The quantity R is called the radius of convergence because in the case of a power series with the complex coefficients, the value of S with absolute of S less than R from an open disk with the radius R. For example, to find the radius of S minus 4 to the n over n, first we need to take the ratio test, and it will end up with S minus 4. In order to this power series get converges, S minus 4 need to be less than 1, and we get S go from 3 to 5. After that, we need to check on the endpoint as S equal 3, the power series become condition converges, and at S equal to 5, the power series get diverges. Therefore, we get 3 less than or equal S less than 5, and the radius is 1.
So for this section, we are going to be talking about the Taylor series expansion. Here we start with the proof of the Taylor series, in which we use the first fundamental theorem of calculus, in which you take the integral from a to x of f prime of x, which equals fx minus fa. This next step, you swap the sides, leaving you with fx equals fa plus this integral. Then take the first derivative. So you have f prime of x equals f prime of a plus integral of a to x, the second derivative of the function. Now you want to just plug in the first derivative back into fx. So you have fx equals fa plus the integral of f prime of x dx. And so here you can evaluate the first integral so that we know f prime of a is a constant since we're integrating with respect to dx. So you can pull that out of the integral, leaving you with fx equals fa plus f prime of a times x minus a plus this double integral in the back. And eventually, if we keep plugging in the first derivative, second derivative, and so on, we'll be able to have this power series here in which it's the nth derivative multiplied by x minus a to the power of n over n factorial. So this slide is just a continued proof of the Taylor expansion, in which we continue with the second derivative of the function and we just plug it back into the double integral. And here you can evaluate the first integral on this line, leaving you with f double prime a multiplied by x minus a squared over 2. And yeah, eventually you can just keep evaluating third derivative, fourth derivative, which leaves you with the series over here. Alright, and this is the Taylor expansion proof. So here's a generalized rule for basically any given function, where you just take the first few derivatives of the function and then evaluate the derivatives at the specific point A, and then you can just write out the expansion from there, where it's like the derivative multiplied by x plus the second derivative multiplied by x squared over 2 factorial, etc., where you'll eventually be able to write out the expansion in a compact form. And depending on what a is, the factorial and square will be different. So it won't always be x squared over 2 factorial, etc. Here we have an example of the Taylor series in which we have a given function y equals e to the power of x, and we're trying to find the Taylor series expansion. So the first step would be to take the first few derivatives of the function, like so. For e to the x, all the derivatives are exactly the same. So for simplicity's sake, we'll use our a as equal to 0. And so we evaluate all the derivatives at a equals 0, leaving you with 1 for f of 0, f prime of 0, etc. This is also actually a special case called the Maclaurin series, in which, yeah, a is 0. And here we use the evaluated values of f prime of 0, f prime of double prime 0, etc., to write out the expansion. And so that leaves us, for this function e to the x, the Taylor series would be e to the x equals to 1 plus 1 times x plus 1 times x squared over 2 factorial, etc., since a equals 0 in this case. Eventually, if we keep going, we'll be able to notice a pattern here in which the compact form is the sigma from 0 to infinity x to the power of n over n factorial.
We'll learn about decomposition. E to the power of ix equal to 1 plus I x over 1 factorial minus x squared over 2 factorial minus I x to the third over 3 factorial, etc. And then we could see that the pattern is I to the power of n times x to the power of n over n factorial. Then we could see from the equation of e to the power of ix that we could separate ex into 2 parts. E to the power of x equal to square bracket 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial, and etc. And then we could see the pattern that it forms into minus 1 to the power of n times x to the power of 2n over 2n factorial plus I square bracket x to the over 1 factorial minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial, etc. plus minus 1 to the power of n plus 1 times x to the power of 2n plus 1 over 2n factorial. And then it forms the equation of e to the power of ix equal to cosine x plus I sine x. and we could see that e to the power of x is equal to the power of series of from 0 to n of minus 1 to the power of n times x to the power of 2n over 2n factorial plus I, the power of series from 0 to n of minus 1 to the power of n plus 1 times x to the power of 2n plus 1 over 2n plus 1 factorial. And we could conclude that cosine x is equal to the power of series from 0 to n of minus 1 times x to the power of 2n over 2n factorial, and sine x is equal to the power of series from 0 to n of minus 1 to the power of n plus 1 times x to the 2n plus 1 over 2n plus 1 factorial. We will learn about substitution. We know from our pre-calculus class that the power of series of 0 to n of x to the power of n is equal to 1 over 1 minus x. Hence, using the power series, we could find the summation of other equations. The first one is 1 over 1 plus x. We substitute x with minus x, then the equation will be the power of series from 0 to n of minus 1 to the power of n times x to the power of n. The second one is 1 over 1 minus x squared. We substitute x with x squared, then the equation will be the power of series from 0 to n of x to the power of 2n. And the third one is 1 over 1 plus x squared. We substitute x with minus x squared, then the equation will be the power of series from 0 to n of minus 1 to the power of n times x to the power of 2n.
And next we will look at the integration of power summation. So from pre-calc, we learned that the integration of 1 over 1 minus x would equal to minus ln of 1 minus x plus c. And hence, using integration, we could also find the power summation for each of these equations. First off, we have ln 1 minus x. So if we integrate minus 1 over 1 minus x, we could also find that the power summation of ln 1 minus x equals to minus the power series from 0 to n of x to the power of n plus 1 over n plus 1. Also, to find ln 1 plus x, we could find it through the integration of 1 over 1 plus x. Hence, we get the power summation of 0 to n of x to the power of n plus 1 over n plus 1. And afterwards, we could also find the power series of arctangent x through the integral of 1 over 1 plus x squared. That would equal to the power series from 0 to n of minus 1 to the power of n times x to the power of 2n plus 1 over 2n plus 1.
Next, we're gonna talk about differentiation of power series. From decomposition of power series for cosine of x and sine of x, we already have cosine of x is equal to sigma and goes to from 0 to infinity, negative 1 to the n to the 2n over 2n factorial, and sine of x is equal to sigma negative 1 to the n plus 1, x to the n plus 1 over n plus 1 factorial. In this example, we take differentiation of sine of x in order to get the power series of sine of x. When we take a differentiation of sine of x, we can get sigma n goes to, or n goes from 0 to infinity, negative 1 to the n to the 2n over 2n factorial, which is same as what we got in the decomposition of power series. Next, we're gonna talk about combination of power series. In this example, we are going to use the combination of x arctangent of x. First of all, we are going to get the power series of arctangent of x. As we know, we can use 1 over 1 minus x is equal to sigma n goes from 1 to infinity n to the n. When we substitute n to the negative x squared, we get 1 over 1 plus x squared is equal to sigma negative 1 to the n x to the 2n. Next, we take integration for both sides. Integration of 1 over 1 plus x squared dx is equal to arctangent of x. Finally, we multiply x to the both sides, and we can get x arctangent of x is equal to sigma negative 1 x to the 2n plus x over 2n plus 1, like this example. In this another example for combination for power of series, we wanna get xn of x. What we can do first is we take differentiation of cosine of x in order to get this power of series of sine of x. When we take a differentiation of cosine of x, we can get sigma n goes from 0 to infinity, negative 1 to the n plus 1, x to the n plus 1 over n plus 1 factorial. So in order to get xn of x for power of series, we basically multiply x to the both sides. Then we can get x sine of x is equal to sigma negative 1 to the n plus 1 x to the n plus 1 over n plus 1 factorial, like this example.
And lastly, we will learn about the application of this power series. From the previous slides, we learned that e to the power of x equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power 4 over 4 factorial, and etc. Hence, to apply what we learned to this equation, we could try to find the value of e to the power of 1. By substituting x equals to 1, we could then approximate the value of e to the power of 1, where we could add 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus etc. We could continue to add the terms until we reach the desired accuracy. And for this, we get the approximate that e to the power of 1 equals to 2.718.
For watching.